All right, so today we're going to start a new topic, and that is called sequences. So many of you would have probably already know a thing or two about sequences. Many of you may have already met this stuff before. We'll see when we start to study it that a lot of this uh, material, in fact, a lot of this proof is going to be very similar to proofs and material and even the statement of theorems that we saw when we talked about limits. That is because there's a very strong connection between sequences and the idea of limits and convergence. So I'm just going to give you a brief outline of what a sequence is, what it's trying to do, and then we'll look at the more rigorous definition. So we have, for example, the usual notation for functions that you all grew up using. So this is the usual function notation. And this one will be the sequence, right? Notation, or the notation for a sequence. So what do I mean by this? So if we have a function f defined on some set A into R, then a way to think about this is that the function is like a machine labeled f. So f is the name of the function. And we have an input. We usually denote that by x, and x belongs to the set A. And we have an output, and the output of this function, or the image, we usually denote by f of x. And this is, of course, a real number. So this is the usual function notation that you all know of. Now, the notation for a sequence is slightly different. The first thing we need to realize is that sequences are special types of functions. That's the first thing. So here, first thing to note is that sequences are functions, right? Sequences are functions. So here's where things become different. In the usual function notation, the name of the function was f. So you all know you can name functions. F, G, H, E, sine, cosine, right? All of those are name of functions. The name of the function for a sequence, I'm going to name that function x. Now, right away, this might be a bit confusing because in the usual function notation, right, in the usual function notation, x was the input, f was the name. Now, for a sequence, x is the name, right? And this function that I'm calling x, the domain is the set of natural numbers and it's mapping into R. Let's just see. So now the picture for a sequence is we have a machine just like before, but before the machine was named X. Now I'm naming this machine X. And what we threw into the machine before was called X. So I can't use X again. But I know what I'm going to throw into this function because a sequence, by definition, are functions that map from the natural numbers. So I'm going to throw in a n, and this n has to be a natural number, right? And the output, just like before, if my input is x, the output is f of x. If my input is n, the output is x of n, right? Now, the notation that we usually use, instead of x of n, we use the notation simply x sub n. Okay, and the sequence is given by the notation uh, is usually written as either a list. So what do I mean by that? So usually we will write the sequence as a list. For example, I list out all the elements. So when I write x1, x2, x3, and so on, you all now know what that is. X1 is simply the value that I get from my sequence when I plug 1 in. X2 is simply the value of my sequence I get when I plug 2 in, and so on. Okay. And this we could sometimes write as simply xn. Sometimes you see this notation, xn, and then they say n goes from 1 to infinity. Sometimes you see this notation, xn. Sometimes you see this notation, xn, as n goes from 1 to infinity, right? All of these are valid notations for a sequence, and you need to be familiar with all of them because many authors use many different notations. Okay, so all of these notations are widely used. So the main difference is that a sequence, yes, it is a function, but again, the main difference is it's just a function that takes any natural number and gives you a new number. The name of the sequence is what we usually call x, not the input. The input is a natural number n. The output is x of n, and we usually don't write x of n. We write x sub n. So x sub n is the value you get when you plug n into this sequence. Okay, so that's the first distinction between it. So what are some examples of sequences? So many of these you may have met before. Let's just list some examples and we'll see that some sequences have different properties. Um, so let me call this first sequence xn. And for this sequence, it's going to be, let's say, 1.5, a third, a quarter, and so on. Right? So this is one way we could write a sequence, like a list of the elements. Or if I wanted to, I could give you the general formula for that element, if there exists one. So in this case, the general formula is simply 1 over n. Okay? So notice that this particular sequence x, all of the values, well, all of the values of the sequence are what we call the range of the sequence. It's just a list of all possible values it could take. So the range of the sequence lies between 0 and 1. Okay, and we'll see in a bit what this means. This is what we will call a bounded sequence. What about this sequence? So I'll call this guy a different name, maybe yn. This one is going to do -1, 0, 1, -1, 0, 1, and so on. Okay, so again, notice that the range of the sequence, all possible values the sequence could take, is just three numbers because it could either be a plus 1, -1, or 0. Okay, so the range of the sequence is again bounded like x. But this sequence seems to be oscillating between three numbers, -1, 0, and 1. What about this sequence, Zn? And I'll do 1, 2, Let's do the easiest sequence. 1, 2, 3, 4, 5, 6, and so on. Right? And of course, the general formula for the sequence is simply n. So this sequence, we see that the range, the list of all possible values it could take, happens to be all the natural numbers. And this particular sequence, Zn, notice that it's not bounded, right? It keeps getting bigger and bigger and bigger. It's increasing, right? And this was what we will eventually call an increasing sequence because each term is bigger than the one before it. But notice something special about this sequence, xn, is that as n gets very large, so we could say as n goes to infinity because now we know a little bit about limits. Um, the terms in my sequence, which we know how to write that's xn, that's the terms in my sequence. As n gets very large, these terms, one, a half, a third, a quarter, and so on, seems to be getting closer and closer to one particular number. They seem to be getting closer to zero. Okay, so for this particular sequence, xn, it seems that this sequence has the idea of convergence, right? Which is something we saw when we talked about limit. The limit of a function as x approaches the value, or maybe as x approaches infinity, is a fixed number uh, where all those function values seem to be approaching, right? Or it's a limit point. So I want to, in a similar sense, use the idea of limits, but now apply it to sequences. So how could we do that? So let's see if we could use a similar idea for limits and attach it to sequences to tell us when are the terms of my sequence converging to some number. So we'll use the same example, xn, and then we'll look at the general definition for convergence. Okay, so I'll put 0 all the way to the left, right? So this is 0, right? That's the value we suspect it's approaching. And maybe over here is 1, and then we go to a half. So these represent the terms of my sequence. 1, a half, right? So I'm not drawing it to scale, but you get the idea. A third, a quarter, a fifth, and so on. Right? So the term seems to be approaching the sky zero. So how do we want to essentially write a rigorous definition for the idea of convergence of a sequence? So when we spoke about limit, if you think back, the definition of a limit, there was an epsilon, right? So for every epsilon, there exists a delta such that, and then you had a bunch of conditions. In this case, we sort of have the same sort of epsilon, um, but it's used in pretty much the same way, except we don't really have a delta. We have a natural number. So for example, if in this particular case, this sequence is indeed convergent to zero. So I could say, for example, for any epsilon that I give you, if you take a term in this sequence, far out enough, then there will be a term, let's call him x big N. So big N is fixed, such that all terms after it, so x big N plus 1, x big N plus 2, and so on, the distance between those terms and this limit will be within epsilon. So how do I say the distance between all those terms that come after x big N, such that the distance, well, I could write it like this, such that the distance of all xn to 0, right? We know how to interpret this. This is the distance of xn. The distance between xn and 0 is within epsilon. For n, so what is this n? This n is a natural number. And when is this true? When is this true? This is true so long as I take natural numbers bigger than this fixed guy, n, right? Because if xn was over here, switch to a new color, then here's xn plus 1, right? Here's xn plus 2. So you see, so long as you take terms ahead of this particular value, x big N, so long as you take terms ahead of this guy, the distance between those terms and this limit will be within epsilon. And this should work for any epsilon I give you. So no matter how small I make this epsilon, you should always be able to find this special natural number, big N, right? You should always be able to find a special natural number such that if you take terms ahead of it, the distance between those terms and the value the sequence is approaching should be less than that epsilon. This is the idea of convergence with sequences. This is how to check for convergence of a sequence. Okay, so the role of this big N takes the role of the delta in the limit definition. So the limit definition we had for every epsilon, we have that if over here. There exists a delta. We don't have a delta, but we have a natural number, N. Right? So that's why I said at the beginning, there's a very strong link between sequences and limits. Okay, so that's the overview. So now we could jump into the slides and we could formalize and make rigorous all of those things. Yeah, so here is that definition, but it's now written for a general sequence. So the sequence I wrote it there was for 1, a half, a third, a quarter, and so on. This is for any sequence. So it's saying that a sequence xn of real numbers is said to converge to another number, x. So when we were studying limits, the value the limit was convergent to, we would call that big L, right? L for limit. In this case, we are calling that number x. So x is a fixed number, right? And what does this mean? It means if for any epsilon, there exists, so no longer delta, but there exists a natural number, big N, so big N is fixed, such that if you take any other natural number, little n, where this natural number is bigger than this capital N, the distance between those corresponding terms and this number, x, this limit, is within epsilon distance. Okay, so for example, if big N happens to be 10, what this is saying is that if you take any term ahead of 10, so if you look at x11, x12, x100, x1000, the distance between those terms and this mystery value, well, it will be a mystery, but this limit x is within whatever epsilon I give you. And if I make epsilon smaller, maybe instead of n being 10, maybe it goes up to 15. I don't know. Then in that case, you will take x16, x17, x18, and so on. So if the sequence xn converges to this value x, then x is called the limit of the sequence. And just like our notation for limits, the limit of f of x is x approaches a or something like that. We have a similar style of writing this, and that is the limit of xn. But in this case, a sequence, when we talk about the limit of a sequence, it's only at n goes to infinity. So when you're dealing with function, x could approach 5, you could approach 7, you could approach 100, you could approach -5. For a sequence, when we talk about the limit, n always goes to infinity, right? So the limit of xn as n goes to infinity is equal to x. Another very common way of writing this that you'll see written a lot is simply xn goes to x as n goes to infinity. So this is another way of writing this. Now, many sequences do not converge. Okay, in fact, two of the three examples that I wrote at the beginning, yeah, yeah, two of these three examples, yn and zn, these don't converge, right? So many sequences don't converge. If that is the case, we say that the sequence diverges, all right? And in this above definition, the number n depends on epsilon. So just like we saw with delta when we talked about limits of functions, the delta you got depends on epsilon. In a similar way, the n you get here depends on epsilon. If I change the value of epsilon, then the value of n here is going to change, right? It's not always possible to find n that works for all epsilon. So that sequence that I wrote there, let's try to prove from the definition of convergence of a sequence, let's now try to prove that that particular sequence actually converges to the number 0. Okay, so that means for every epsilon, I need to choose a natural number n such that n is bigger than 1 over epsilon. So again, when you're doing this proof for the first time, you will not know the relation between n and epsilon. Just like when you're doing the epsilon delta proofs, before you complete the proof, you will not know the relation between epsilon and delta. Only in the last line of the proof would you be able to figure out this relationship. Okay, so if you have a 1 there, how do they know beforehand to take n bigger than 1 over epsilon? They don't know beforehand to do this. They do the proof once, see what goes on in the last line, or they will get a relation between n and epsilon, and then they just solve that for n. Okay, so you'll leave an empty space here, do the proof, and then fill it back out. Okay, so we're going to choose a natural number. Then for any other natural number, little n, and what's the condition of these natural numbers, little n? They must be bigger than this fixed n. So in this proof, what are fixed? Epsilon is fixed and big N is fixed, right? Two things are fixed. What is my target? I need to show that the distance or the modulus between these terms, xn, and the limit, in this case, the limit is 0, is less than some fixed value. That fixed value I will call epsilon, okay? So the distance between xn and 0 Well, what is xn? For this particular sequence, xn is simply 1 over n. So I could plug that in over here. And the modulus of 1 over n, well, 1 over n is always positive. So I could remove the modulus. And notice that if n, what do I have there? No. If little n is bigger than big N, if little n is bigger than big N, then if I invert both sides, I get 1 over n is less than 1 over big N. Okay, so that's how we went from this line to this line. 1 over n is less than or equal, right? If you're less than, then you're also less than or equal. It doesn't matter. And 1 over n, remember I told you all that n is fixed. So 1 over n is fixed. So in this last line, I'm going to set this equal, oh sorry, not equal, less than epsilon. So from this line, I will get 1 over n is less than epsilon, but I need to solve for big N. So solve this inequality. So if I flip both sides, I get n greater than 1 over epsilon. And then this is what we will then take and plug in up here. Okay, so that's a proof, right? Very straightforward proof. Okay. So in other words, xn goes to 0. So technically I should put as n goes to infinity. So now I give you some examples of what exactly this is trying to say. So for example, if I say I want you to find for me terms of this sequence, this particular sequence, 1 over n, that is within a distance 0.4 of the limit. The limit in this case is 0. Then you will say, okay, no problem, because I now have a relationship between epsilon and big N. So you will take that epsilon and you will plug it into that relationship and you will find that big N should be greater than 2.5. Now remember, big N is a natural number. So what is the natural number? What is the next natural number up from 2.5? Well, it's 3. In other words, if I take x3, x4, x5, so if I take from x3, go up, then the distance between these terms and 0 will be within epsilon equal, for this case, it's 0.4. Okay, so what happens if I now change epsilon? What if now I say, okay, I want terms even closer to this limit. I want terms 0.2 close. Then you say again, okay, no problem. You take that 0.2, you plug it into the relation for n and epsilon, and now you get n must be strictly bigger than 5. So what is the next natural number up from 5? Well, it's 6. So now you will say you just need to take from x6, x7, x8, and these terms, the distance between these terms and 0 will be within epsilon equals 0.2. And no matter how small I make epsilon, you could always find a natural number, big N, and tell me, as long as you take terms bigger than this guy, ahead of this big N, the distance between those terms and this limit, in this case it's 0, will be within that range you're looking for. Okay, that's the idea of this limit. Okay, so what about, so that's if the sequence converge, but in reality, if you have a box that contains all possible sequence and you put your hand in that box and you pick a sequence at random, there is 100% chance that that sequence you chose at random is divergent. So there are much more divergent sequences than convergent ones. Of course, they are both infinite, but okay. So let uh, xn equal 1 plus 1 minus 1 to the n. We're going to show that this sequence is divergent. So usually when you're given a sequence like this, it's always a good idea to write out some of the terms. So when n is equal to 1, plug n equal 1 into the sequence. So you get 1 plus minus 1, which is 0. Then plug n equal 2. So you get minus 1 squared, which is 1. 1 plus 1 is 2. Then plug n equal 3. So you'll quickly see that for odd values of n, the sequence is 0. And for even values of n, the sequence is 2, right? So clearly the sequence is bouncing back and forth between 0 to 0 2. So it's not going to be convergent. Okay, so I'm going to assume that it is convergent, and let's see what happens. So I'm going to assume that there is some value, x, some real number, that this sequence is indeed convergent to. So that means for any epsilon I choose, I should be able to find a term in this sequence such that if I take terms after it, the distance between all those terms and this mystery number, x, will be within any epsilon I choose. So why don't I choose epsilon to be 1? Okay, so I'm going to choose epsilon to be 1, and I'm now going to argue that no such um, uh, big N will get me within a distance of 1. Okay, then that means there must exist some big N such that if I take any other natural number ahead of this big N, the distance between those terms and x should be within 1, right? This is the definition of a limit of a sequence. All I did was I just took epsilon equal 1. Okay, but we have two cases. If n is odd, then I know that my terms are all 0. Okay, if n is odd, then this term here is 0, right? So that's what they're working out here. This is 0. So I get modulus x must be less than 1. And of course, you all know what this means. It means x is between plus and minus 1. So this is if n is odd. If n is odd, because remember, we don't know what this limit is. This limit is a mystery. So if n is odd, then this mystery limit should be a number between minus 1 and 1. Okay, let's see what happens if I say n is even. Right? If n now is even, then we know that this term is equal to 2. Right? This is equal to 2. So I get the modulus of 2 minus x is less than 1. Right? And of course, you all know that that means that 2 minus x is between plus 1 and minus 1. Right? And then you will subtract 2 going across. So minus 2 going across. So we get minus 3 is less than minus x is less than minus 1. And then multiply through by minus 1. So I get 1. So the sign changes. 1 is less than x is less than 3. So this is the case if n is even. Okay, but it should work for all n. So for natural numbers bigger than this big N, well, obviously those natural numbers contain odd and even natural numbers. But if n is odd, it's telling me that this mystery limit is between -1 and +1. If n is even, it's telling me this mystery limit better be between 1 and 3, right? So there is no value that in these two range, right? There's no value in these two range. So for any natural number n, that means x should be a value in this range. But this range is empty. Okay, so therefore this is a contradiction. So the sequence must be divergent because the only thing I assumed from the beginning was that the sequence converges to some mystery value n, and I showed that, sorry, some mystery value x, and we showed that no possible x can exist. Okay. So just like we saw with limits, if the limit exists, it was unique, right? So go back and so in all the proofs in this section, you should go back and check the similar proof in the last chapter. Because if you know one of these proofs, then you know the other one. So there's no need to learn the same proof twice, right? You just learn the what you need to change, the two little similarities. So this is saying if a sequence of real numbers converge to some limit, there's only one limit you could converge to, right? And you see proof left as an exercise, and I say see proof for uniqueness of limit in chapter 4. This proof is the same proof, except wherever you see in this proof, wherever you see delta, remember there's no delta here, you replace it by x. Sorry, big N, big N, big N. Okay. And wherever you see the limit L, you will of course replace it by x. And wherever you see the function f, that is your xn. Right? So as long as you just replace these values, it should be okay. Now what is a bounded sequence? So one of the sequence that I drew, no, two of them were these things called bounded sequence. So a sequence xn is said to be bounded if its range is a bounded set. Now, what is the range of a sequence? The range of a sequence is just a list of all possible values it could take. Okay, so the list of all possible values a sequence could take could either be finite or infinite. For example, the sequence +1 -1 +1 -1 that we just saw. The range of this sequence is just two numbers. What are all possible values this guy could take? Just two numbers. You're either -1 or +1. Okay. What about this sequence? um, 2, 4, 6, 8, 10, and so on. Okay, so the range of this sequence, yn, in this case, every term in this sequence is unique. So in this case, the range of the sequence is 2, 4, 6, 8, and so on. Right? It is all of the possible terms. Okay. So the definition is saying that a sequence is bounded if the range is a bounded set. So you all know what bounded set means. It has an upper bound and a lower bound. Okay. So of these two sequences, x and y, which one? So we look at the range, right? So we're looking at the range. Which one of these ranges is bounded? Well, it's the first one, right? Because the set containing just -1 and +1 is of course a bounded set, right? It has an upper bound, let's say 10. It has a lower bound, let's say -10. However, the range of yn, yes, it has a lower bound, let's say 0. Every term here is bigger than 0, but there's no upper bound. no upper bound. So Yn is not bounded. Okay, so Yn is not a bounded sequence because bounded means both, both upper bound and lower bound for the range. Now there's another way to write this that's very useful for when we do proofs. And that is to realize that if the range of a sequence is a bounded set, another way of saying that is that every single term of the sequence must be between some number, right? It means every single term of the sequence must lie between plus or minus some number m. Okay, so in our example xn, notice that every xn lies between, let's just say, so remember the bounds doesn't have to be like really tight bounds. They could be any bound. Notice this lies between 2 and 2, right? For yn, yes, all the terms of yn are bigger, let's say, than 0, but there's no upper bound, right? Right, and of course, you'll know another way of writing this is simply saying that the modulus of xn is less than or equal to m. That is what this is saying. They're saying equivalently, xn is said to be a bounded sequence if there exists some positive number m such that the magnitude of all these terms is less than or equal to m. Okay. So now we want to prove if you have a convergent sequence, then it is a bounded sequence. Okay. So this one follows straight from the definition, like many of the proofs before. So let xn be a convergent sequence, and let the limit of it be this fixed value x. So now we are just going to write the definition of convergence. The definition of convergence says, for every epsilon, I could find a natural number n, so big N is always fixed, such that if I take terms in my sequence ahead of this big N, then the distance between those terms and this mystery number x will be within epsilon. That is the definition of convergence. Okay. So now how are they moving from that line to this line? So now we need to remember some properties of your modulus. There's a property in modulus that goes that the modulus of mod A minus mod B is less than or equal to the modulus of A minus B, right? So this guy here is your A, this guy here is your B. And we also know, so they're using this and a second property of modulus, and that is any number is always less than or equal to its modulus. So in other words, this guy is bigger than mod A minus mod B, right? So to use this, they are using the fact that mod A minus mod B is less than or equal to mod A minus B, right? This is sometimes called reverse triangle inequality, right? So again, this is A and this is B. That's how they got that inequality, okay? And now once we have this inequality, we could sort of ignore this guy in the middle, right? And we could take this x over to the right-hand side. So we get that the modulus of xn is less than or equal to x plus epsilon. But this is a constant. right? X is fixed, epsilon is fixed. The right-hand side is constant, okay? And what are we trying to do? We are trying to show that we could find some positive number m such that all of the terms in my sequence, the magnitude of them are smaller than this guy m. Look, this is the terms in my sequence, and they are smaller than this number. But this inequality does not hold for all n. This one does not hold for all terms in my sequence. This inequality only holds so long as I take terms ahead of big N. So what about all the terms before that big N, right? What about all the terms before? Well, here's what you do. You take M to be the maximum of this, right? So where are they getting this thing from? Modulus x1, modulus x2, modulus xn, and then we see this term appear again. Okay? This term here is what you see here. But what are all of these other terms? Well, what is this sequence? This sequence is x1, x2, x3, all the way up to x big N. What's the guy after x big N? X big N plus 1, x big N plus 2, and it keeps going. What you have just proved here is that all of the terms ahead of x big N, that's these guys, all of these terms are less than mod x plus epsilon. All of them, the magnitude of them are less than mod x plus epsilon. So what about all these terms before? All these terms before, these n terms, big N terms, what are these terms less than? Well, x1 is less than or equal to mod x1. x2 is less than or equal to mod x2. x3 is less than or equal to mod x3, and so on. X big N is less than or equal to mod x big N. So all I need to do is take the minimum of mod x1, sorry, the maximum, the maximum of mod x1, mod x2, mod x3, mod xn, and this last guy. If I take the largest of all these values, and these are finitely many values, for example, if big N was 10, then these are just 11 numbers. So look at these 11 numbers, choose the maximum. Then that maximum I'm calling big M, which will guarantee that x1 is now less than big M, x2 is less than big M, x3 is less than big M, xn is less than big M. All these terms ahead are less than big M. So every term in this sequence is less than M, right? Then all the terms, so the modulus of xn is less than or equal to M for all natural numbers. Therefore, xn is bounded. Right? So very, very important result. Right? So convergent implies bounded. But the converse is not true. Bounded does not mean you converge. Right? So see if you can think of a bounded sequence that does not converge. The next class. Okay.